I think a lot of folks, personal and in their professional life, are looking for ways to impute artificial intelligence and machine learning to help be more productive, augment, get better ROI out of things. And there's a danger. I think people are trying to force it in there when that's not how it should be done. That's just not my opinion. That is just should not be done. When you're holding a hammer, you shouldn't try to make nails. The best, absolute best way I've heard to find the right business use cases to augment or solve problems is to find those problems that haven't been otherwise able to be solved. And that is a lot of times where artificial intelligence and machine learning can really shine. And I'll give you a prime example. Additive manufacturing. There are so many great things about 3D printing. It creates parts as a whole. It can speed up. You can make individual parts much quicker. And that's also its downfall. Because when you create a part as a whole, when you 3D print it, you don't know if it's defective internally. I actually used to work for a aerospace company, and people were constantly exploring how do we use additive manufacturing in this process. And the FAA, time and time again, would deny it because how do you know if it's defective or not? Well, in steps machine learning. And I actually came across this article from the University of Illinois. Researchers use machine learning to detect defects in additive manufacturing. Here's actually, not that article, we'll get to that, but here's the actual article. It's behind a paywall. Can't get to it. But thankfully, there are articles that were published that show some illustrations. So here you see this is a computed tomography or CT scan of it, and then it's able to use computer vision, and you see these isolated red circles identifying the defects. But that's not the really cool, interesting part, because computed tomography has been used in the past. Get away from that. And coincidentally enough, I mean, this is a University of Illinois article, and this other article I have here is an article from Southern Illinois University, Carbondale, practically right down the street. And they've published in the past the ability to use machine learning and computed tomography. But I want to talk about the difference, the really cool difference. So this one relied upon an image data set somewhere. Let me find it. Here it is. The study was carried out with the publicly available XCT image dataset of additively manufactured cobalt chrome specimens. That's super specific. For training computer vision models, you can train a lot of times using large publicly available image datasets, and they do what's called transfer learning. Augment your training by adding some additional image datasets, and that way it has a much larger pool to pull from. That can become a problem. And, you know, it did work in this case, goes through all the architecture in this, shows how the model is actually built out. You can see all the layers, the hidden layers, the pooling, everything that convolutional neural networks use in computer vision models. I won't go too in depth that. It worked. It was able to identify with fairly high accuracy. But what if you have like a really specific part? You really want to zero in and accelerate the ability to train on the specific part that you are creating. And that's where this abstract comes in. This is the really cool part. They trained on computer generated images. So this is a supervised learning technique where they had a computer synthetic generated image data set that was free of defects of the part, different CT scans, and then they had a data set that was labeled as defective. And supervised learning, when you're able to train the model, just you tell the model, this is what defective looks like, this is what defect free looks like, and then that's how it trains. So then they were able to take the actual CT images of the part and with, I believe it was 90% accuracy, determine whether or not something was defective or not defective. And I think the ability to not have to rely upon publicly available, very specified training data sets. And then also, here's an issue. Imbalanced data sets. Generally, when you're looking for whatever it is that you're trying to identify, you have much less of that especially in this, we'll say images, than you would the ones that are free of defects. So it creates an imbalance. There's weight issues, and you have to do some oversampling or undersampling. And that can cause a lot of issues because you really have to train the model and figure out where performance is best. Different Python libraries help out with that. But if you can create, in this instance, an even number of defective versus defect-free images, you don't have to worry about the sampling issues. And I think that's why this is really interesting to speed up. Generally, I'm worried about the use of synthetic images to train anything, but this is a specific instance where that's wrong. It actually has a great use case. And again, the problem has long been in additive manufacturing, you can't look under the hood. It comes out as one solid piece, but with the ability of using CT scans in conjunction of speeding up the process, not getting under the microscope with individual images, you're able to quickly identify where the defects are. Problem solved with AI.